Okay. Good evening. Nice to see you to our third edition of the Distinguished Lecture Series in Business Analytics and Data Science. Today, Arne will be presenting. Arne is our first professor we actually studied here at KLU. He's professor for transportation and he has published in the best journals that are around in transportation, I would say. And he's going to present about machine learning for optimization, a topic that I'm very interested in, and I hope you are as well. So please, Arne.
Well, thanks a lot, Aswin. And happy to see you all here offline, online. And I'm happy to talk today about learning to optimize, so how machine learning drives decisions at companies like Uber. So I won't present any company secrets here today, but I will explain you how decisions are made at companies like Uber. And I would like to start with a short motivation by showing you a video what Uber actually is. So let's take a look at this 2.5-minute video.
Uber is a technology company that connects riders to driver partners at the push of a button. Since 2011, Uber has been creating flexible work opportunities across the United States by partnering with driver partners like you to provide reliable and affordable transportation.
Whether people are requesting rides in a major metropolis like New York, Dallas, or Seattle, or tighter-knit communities like Baton Rouge, Omaha, or Fresno.
From the south side of Chicago to the Bay Area.
From Atlanta to Albuquerque, Portland to Pittsburgh.
Riders are looking to Uber to connect them with a safe ride when they need one.
We knew everyone could use some extra cash. Whether you're working to supplement your income or save for a vacation, we have a dedicated team in cities across the country working hard to help you get on the road and earning as quickly as possible.
And when you hit the road, we'll make sure you always know the best times and places to drive. Our goal is to help you maximize your earnings while driving with Uber.
And if you need us, we have support options that are available 24 hours a day, 7 days a week, 365 days a year. We want you to know that Uber has your back.
Whether riders are headed to the big game, a night out of the town, or trying to find an easy way to get to the airport, our marketing team will ensure riders know Uber is an option wherever they go.
We couldn't be more excited that you've chosen to partner with us. By driving with Uber, you can be your own boss, set your own schedule, and earn extra money by helping people get around their cities safely. I'm Ian Black, and I'm the United States Regional General Manager for Uber.
Welcome.
Welcome to Uber. Welcome to Uber.
Welcome to Uber.
Welcome to Uber. Work that puts you first.
So that is the company Uber. And I actually brought some quotes from that video that will show us a little bit of what kind of decisions are made at companies like Uber. So as we have learned in that video, Uber is a technology company that connects riders to driver partners at the push of a button. So at the push of a button means they do it in milliseconds. So they have to make very, very fast, quick decisions. They also say whenever people are requesting rides in major metropolis or tighter knit communities, riders are looking to Uber to connect them with a safe ride when they need one. So they promise to provide you with an offer. Third quote, when you, so the driver, hit the road, we will make sure you always know the best times and places to drive. And in order to find out where are the best places to drive and what are the best times, well, they use technology and they use machine learning. And the final quote, whenever riders are headed to the big game or night out on the town, we will make sure riders at Uber have an option wherever they go. So this company is essentially promising quite a lot. And they fulfill their promises through their app. And the Uber app claims, push a button, get a ride anywhere. So what you essentially do, you go to that app, you type in your origin and your destination, and the app will provide you at the push of a button with a list of available vehicles and also the rates. And you select the vehicle, and then that vehicle arrives to pick you up. And today we will look what happens behind the scenes when you actually push that button. So here's the problem. To understand how the problems in companies like Uber are solved, we need to understand the nature of the problems. And for that, I would like to introduce 4 terms and define those terms to understand the nature of the problems and how to solve them. And the first differentiation is between a stochastic and a deterministic problem. And to illustrate that, I thought about the example of a bus. So you see here this yellow bus. It could be a school bus or any bus traveling around the city. And in a stochastic problem, we have a problem with some uncertainties. So, for example, we know the stops of the bus, but at each stop, we do not know who's going to enter or exit at that stop. So we have a person with a cane, we have a person in a wheelchair, we have a person pushing a baby stroller, an adult with 2 children, and a family with 2 adults and 2 children. But the trick is we do not know when they enter or exit the bus. In contrast, in a deterministic problem, we are talking about problems with full knowledge. So we have so-called perfect information. So we know that at the first stop, there will be the person with the cane and the person in the wheelchair entering our bus. And at the third stop, there will be that person with the baby. So that is the differentiation between stochastic and dynamic. And clearly, in the context of Uber, we have a highly stochastic problem. Right? So they do not know when customers push that button. They do not know, or they have some uncertainty regarding the traffic conditions and many, many more uncertainties I will talk about later on in this presentation. Now, that is the first differentiation. The second differentiation is between dynamic and static problems. So in a dynamic problem, we're talking about a problem that spans over multiple periods or stages. And in those problems, decisions are taken sequentially. So considering our bus again, we know that we have to decide at each stop to accept or reject customer requests. So for example, that person in a wheelchair, we can accept that because capacity allows it. But for the person with a baby, we have to reject that request because our bus is already full. And then we can accept the person with a cane. That's a 4th stop. Now, in a static problem, we have only a problem in a single stage or single period. So all decisions are taken at once. So for example, when the bus stops in front of our university in the Hafen city, we can decide, or we have to make decisions for all of those passengers. And again, we could decide to accept 2 of them and reject 1 of them. So when we talk about problems like Uber, well, we talk about dynamic problems. So we have to make decisions step by step, sequentially. And when we look at problems like Uber, we can compare them to one of the classic optimization problems in logistics and transportation, the so-called vehicle routing problem. So imagine you have a fleet of vehicles and a set of customers who need deliveries. The goal of the vehicle routing problem, or VRP, is to determine the most efficient routes for the vehicles to take so that all customers are served while minimizing the total travel distance or cost. So essentially, it's about finding the best way to get goods from a central depot to various locations in the most efficient manner. And it involves an assignment problem, so we need to match customers with vehicles, but also a routing problem where we have to actually find the shortest path. And we can use this very simple problem, which is already hard to solve, and try to understand what makes it even more complicated for companies like Uber. So in the static version and the deterministic version, which is the bottom left corner of this matrix, we have the basic version of the vehicle routing problem. If we add some uncertainty, like uncertainty regarding the locations or the quantity transported or the time windows, we have an even more complicated problem. If we then look at this problem in a dynamic way, we have to not only solve that problem once, which is already challenging, but we have to solve it many, many, many times. And if you combine those 2 elements, we have a stochastic and dynamic problem, which is among the hardest problems to solve an optimization. And that's what we are talking about at companies like Uber. So very, very complicated, complex problems where we need very smart ways of solving them. And we use a framework to describe them. And I would like to explain the framework, it's called sequential decision processes, to you by using a very simple example that we probably all know. And that is a game. And the game is called tic-tac-toe. So let's take a look at this 1-minute video. You see this transcript on the right part of the slide to understand what this game is all about.
Tic-tac-toe is a fun 2-player game where players try to get 3 of their symbol, either X or O, in a row before their opponent is able to. To play the game, first draw a 3x3 grid, so there are 9 open spaces in total. Then decide who will use X's and who will use O's. Take turns writing your symbol in one of the open spaces on the grid. Try to get 3 of your symbols in a row while also blocking your opponent from getting 3 of their symbols in a row. Whoever gets 3 of their symbols in a row first wins. If no player gets 3 in a row, it's a draw, and the game starts over with a new empty grid.
So that is a game, very simple. And interestingly, this game has a long history. So it traces back to ancient Egypt, where 3x3 grid games have been found on drawings 1,300 years, or 1,300 BC, so nearly 3,000 years ago. And early variations of this game has also been recorded and played by the Romans with a little twist. So instead of having at most 9 pieces to put on the board, there were only 3 pieces which you could use again and again. So you were shifting around the pieces, making this game a little bit more interesting. But we will use the game tic-tac-toe to understand how machine learning works. And once we have understood that, we can apply that knowledge to understand how problems at companies like Uber are solved. So essentially, tic-tac-toe is a paper and pencil game for 2 players. Now, to understand the framework, I will introduce a few terms. And the first term that I'm going to introduce is called a state. So the term state refers to the properties or characteristics that are associated to this point in time before making a decision. So what we essentially do in a state, we hit the pause button for the reality. So when we push that button, everything freezes. And we take a look at what is happening right now. And this freezing moment could be time-based, like we could say stop the system at 6:15, or it could be event-based, like customer arrives, order is received, or customer pushes the button. So whenever that is the case, we pause everything, analyze the status quo, and that is called a state. So the meaning for tic-tac-toe is that we can consider the board as a state. So a possible 7-step game with 8 states could look like this. So we start with an empty grid, then the first player positions or places the mark in the top right corner, giving us a new state. So based on that, the second player, player O, moves to the top left corner, giving us a new state for player X. And that essentially moves on and on and on until finally, in this case, player X wins the game. And this is a state. And the question we are trying to answer is, what is the best move? So what is the best decision? Similar to what we see in transportation problems. So, how many states are there? And this is a video showing you all of the possible states for the tic-tac-toe game. You want to guess how many states there are for this simple game?
2 to the power of.
Yeah, it's tricky. It also depends. It also depends a little bit on how you look at the game. So if you consider rotations, if you consider reflections, then there are less states. So depending on how you look at this question, there can be between 700 all the way up to 20,000 states. But what we do know, there are 26,000 possible games, so possible ways to play that game. Now, at each of those states, we need to find a smart way to select the best decision. And that brings us to the next essential definition called decision. So a decision is also called action or move, depending on the community where you're working. So a decision is, given a state, it is a possible action or move, such as order 500 pieces, or accept that customer, reject that customer, or place your mark in one of those cells. So given this exemplary state for tic-tac-toe, where player X has 3 crosses, one in the top center, one in the center itself, and one in the bottom right corner, and O has 2 O's, one in the top left corner and one in the bottom center cell, there are 4 possible decisions. So either going to the top right corner, going to the center left cell, going to the center right cell, or going to the bottom left cell. So 4 possible decisions. But which one is the best decision? And that is what we want to find out. And the twist with the tic-tac-toe game is that we actually only find it out at the very end of the game. So either we win or we lose. So that's a little bit different with companies like Uber. They have an immediate reward, but it might not be optimal to always be greedy in that sense, but we'll talk about that later. All right, so we have the state where we hit the pause button, freeze everything, observe, and in that moment of pause, we make a decision. So the next step is the so-called transition. So the transition happens after the decision. So given the state and a decision, the transition function describes how the next state is reached. And that is where the uncertainty comes into play. So we at Uber, we have made a decision, but then there's a traffic jam. Or then there's another customer approaching us. Or the car is not working. So many different uncertainties. Regarding the game tic-tac-toe, the uncertainty is about the opponent's move. So given the following state, an O's decision of placing the mark in the top right corner, the transition function now simulates the uncertain decision of the other player. So in this case, player X moving to the center left cell. All right, so we have the state, we have the decision, and we have the transition. So that's everything we need to know. And now we can define our optimal policy. So our policy is essentially the behavior, what we do. So given a state and a policy, or given a state and a decision, a policy describes a decision taken from the total set of possible decisions. And a decision policy can be very simple. For example, when we talk about stock markets, it can be selling when the price is above or below a certain limit, like €5. But it can also be very complicated using mathematical programming. So I played the game tic-tac-toe quite often in my classes with students, and the policy often used by students looks like this. First, they try to win. So if they have 2 in a row, they place the third one, or the third mark, to get 3 in a row and win the game. If that is not possible, they try to block. So if the opponent has 2 in a row, they block the opponent. If that is not possible, they hope. They place such that they have 2 in a row and the opportunity to win in the next turn. And if that is also not possible, well, they play a random move. But this is not the optimal policy. In fact, if you follow the optimal policy, the game, or you will always win, or at least there will be a draw. So here's the perfect game when you want to play tic-tac-toe. And it's quite an old figure because, well, it's quite an old article. And this optimal policy is not just a 4-step process, but it's actually a 7-step process. So first, you try to win, right? Similar as what students do. Then you try to block, obviously. But then there comes a new move called a fork. And that is something players usually oversee. So a fork means that you create a scenario where you have 2 ways to win on your next turn. So consider this state where we have 2 X's, one in the top left corner and one in the center right cell, and 2 O's, one in the top right cell and one in the bottom center cell. You can create a cork as player X by going to the center. So in this way, you have 2 ways to win, and you essentially will win with your next move, right? So if it's not possible for you to create a fork, you should try to block a fork. But as you see already by the size of this box, identifying how to block a fork from your opponent, that's quite tricky. Well, if that is not possible, you should play center. That's why every good player starts by playing center. If that is not possible, play the opposite corner. If that is not possible, play the empty corner. And if that is not possible, play an empty side. So that is the optimal strategy. So when both players follow that strategy, there will be a draw. But whenever one player is not following that strategy, you have the opportunity to win. But obviously, computers can't really learn the words as we see them here. But we have to teach the computer a little bit differently. And I will show you that in the next section. So the key takeaway from this first part of this lecture is that a sequential decision process is described by a state, or by states, by decisions, by transitions, and by policies. So how do we solve those problems? How do we solve the tic-tac-toe game? How do we teach the computer how to play that game following an optimal strategy? And how can we use that knowledge to solve problems at companies like Uber? Now, let's simplify the Uber problem. And for that, I will use a taxi cab problem. And the taxi cab problem is a type of optimization problem where a taxi service needs to decide which customers to serve within a limited operational time frame. So it's essentially just one driver. One driver, one city, and a few customers. And it's a simplified version of Uber, but we can use that to demonstrate how those machine learning algorithms work. So here's the situation. We have a city, and you see the city, a sketch of the city on the right part of the slide. We have a temple, a warehouse, a power plant. We have a town hall, a factory, a church, an office tower, and a suburb area. And the arcs in this figure, they show the profit. So for example, there's one customer request from the temple to the warehouse, and that would bring us an immediate profit of 15 euro. If we look at the request from the temple to the factory, that one will give us an immediate reward of 30. And the taxi driver now sees all the waiting customers at its current location, but also at other locations. And the taxi needs to decide which ones to take from its current location or going to another location and picking that customer up there. Now, in a static one-period problem, we obviously take the trip with the highest immediate profit. So in this case, going to the office tower. So going from the temple to the office tower will bring us an immediate reward of 40. But also for companies like Uber, and especially for this taxi driver, it is a dynamic problem. So it's not just important how much profit do we get right now, but also what is our future profit. And finding out the value of the future profit at a specific location is tricky to find out. And we can use machine learning to find out the value of that future profit. So let's take a look at this example. So the taxi driver starts at the temple, and for some reason he decides to go to the warehouse. So he was greedy. He gets an immediate profit of 18 by going to the warehouse instead of going to the office tower, where he would have got an immediate profit of 17. Now, in period 2, if the taxi had been traveling to the office tower in the previous period, it would have had the possibility to go to the suburb with high profit. So it would have been clearly better, in this case, to not following the greedy strategy, going to the warehouse, but rather going to the office tower. But he decides now to learn from his or her mistake, and instead of going to the warehouse, the taxi driver, instead of going from the warehouse to the town hall with an immediate profit of 8, well, the warehouse thinks, the taxi thinks about going to the power plant with an immediate profit of 5. But the taxi driver was unlucky because the profit that was there in the previous period between the power plant and the factory, well, it's not there anymore. So probably another taxi has served that request. And, well, if the taxi were not at the power plant, it would have more options for immediate profit. Now, he learns from that mistake, now decides to wait at the power plant, and luckily, there is now a new profitable trip to the factory, bringing the taxi an immediate reward of 10. Now, we have that problem for one taxi in one city, but in reality, it's obviously a little bit more complicated. And science has come up with 4 general ways of solving problems like this. And those solution approaches are called in the community of approximate dynamic programming, which is the operations research community where I'm coming from, policy function approximation, look-ahead policy, cost function approximation, value function approximation. And the interesting thing is that each policy class is generally capable of outperforming the others. So not one of them is the best, but depending on the specific problem at hand, each one of those can be the best choice. And a good decision maker therefore needs to know about all of those policies, which is why we at KLU in our new program teach all of those policies. So it's not just important to understand the math behind each of those approaches, but it's also to understand the nature of the problem. So we really need to combine both elements here. But today we will focus on a solution approach called value function approximation or reinforcement learning, because that belongs to the field of machine learning. And the basic idea of value function approximation is that given a state, select a trip from the current position with the highest immediate and future reward. And to know that future reward, we will use machine learning. So let's start with machine learning. So machine learning is a field of study in artificial intelligence concerned with the development and study of statistical algorithms that can learn from data and generalize to unseen data and thus perform tasks without explicit instructions. So what we do in machine learning, we learn from data and generalize. And we do that without explicit instructions. So remember the perfect tic-tac-toe game? That was an explicit instruction, right? It was a very clearly, formal, writtenly down instruction for us human beings to understand how to play the game tic-tac-toe perfectly. Machine learning is following a different approach. They do not write it down, so it's not a rule-based decision-making, but we learn from the data and generalize. So that's why data is so important. Right? That's why companies like operating apps like Instagram or Facebook and so on, that's why I'm so keen about gathering data, because you need data to develop efficient optimization techniques. But today I will talk about reinforcement learning, and reinforcement learning is one of the 3 basic machine learning approaches alongside supervised learning and unsupervised learning. So in contrast to supervised and unsupervised learning, we do not need labeled or unlabeled data, but instead we have an agent, which is here as a robot, that is telling us what to do. And we create an environment where we can learn the value of a decision without actually looking at the real world environment. So what we do in reinforcement learning, we learn the value of an action, and to demonstrate that, I came up with a rule that is called try, learn, and repeat. So that is essentially what reinforcement learning does. So we try by making decisions using the current best prediction. So we're not sure about the perfect rule in tic-tac-toe yet, so let's just try out something. And once we have tried that, we evaluate the outcome and update our prediction. So for example, starting at the center is a good one. So when we play that very often, many times, we learn that starting with the center is actually a very good way of starting the game. So that's why we repeat it. We do it many times. And remember the 26,000 possible states in tic-tac-toe? We only need a fraction of those states to actually understand and learn the perfect game. And that is the magic of machine learning. So let me illustrate you how this try, learn, repeat idea works for the game, and then we look at how it works for the taxicab problem. So for our game, given a current state where player O has 2 marks, so one in the top left corner and one in the middle left corner, and player X has 3 marks, so one in the center top, and one in the bottom right cell. There are obviously, as player O, one way to win the game, and that is going to the bottom left corner. But for a computer, there are 4 possible decisions. So first one is going to the top right corner. So if we do that, well, we probably lose that game, because in the next turn, player X probably goes to the middle, to the bottom center cell, and can then win the game. So that is probably not good. So when we do that, we learn that was not a good move. Second possible move is going to the middle right cell, but same situation. We probably lose that game because player X will choose the bottom center for his or her next move. But if we go to the bottom left corner, we will win that game. So what the machine learning, what the reinforcement learning algorithm does, it will remember that was a good move. Given that state, where we have the X's at those positions and the O's at those positions, going to the bottom left corner will guarantee us a win, so we will always do that when we are in the same state again. And finally, if we go to the...
Sorry, do you want us to close the blinds?
Yeah, that would be nice. Would be easier for me to... So finally, we have a 4th possible move, and that is going to the bottom center location. And being there, we are unsure what's going to happen next because we have blocked the opponent, so we can't win. But at the same time, it's also not guaranteed that we win the game. I think that's okay. Yep, that's better. Thanks.
Trying to find the right move.
Yeah, it's also a stochastic and dynamic process, that's correct. All right, so this is the example with tic-tac-toe, right? So we have a current state, and we try to learn what is the value of each of those decisions in that state. So when we look at the taxicab problem, it looks a little bit more complicated, but similar. So, being at the temple, we could decide to go to the warehouse, which brings us an immediate reward of 18, but only a future reward of 12, or in total a reward of 30. And that future reward, we can't see it, but we can learn it. And that is what we do in machine learning and reinforcement learning. Right? So we play that game very often, and then we learn being in the second period at the warehouse will provide us with a future reward of 12. If we go to the town hall instead, we have no immediate reward. So it appears to be not a good decision. But by trying that out previously, we know that there's a future reward of 45, and with that decision is superior to the decision of going to the warehouse. And we do that essentially for all of those decisions. And here's one more example. So going to the office tower will bring us an immediate reward of 17 and a future reward of 30. So looking at those three decisions on the slide, the best decision would be to go or to move to the office tower. And that is the magic of machine learning. So we try to find out what is the future reward for a possible state. Now let's implement that idea on a slightly larger scale for a larger problem. So what you see here is a matrix. On the horizontal axis you see time periods from 0 to 10. So we play that game, or we play that sequential decision process for 10 time periods. And on the vertical axis you see the vehicle's location. So from A all the way to J. And in that matrix, you see the optimally computed values. So we can compute the optimal expected future reward that is possible for a 10 times 10 grid for a taxi driver being at a particular position in a particular point in time. So for example, the future reward of being at location J in period 9 is 90. And the future reward of being at location D in period 5 is 298. And finally, the future reward of being at location A in period 0 is slightly above 400, which is the expected value following an optimal policy. So we know that this is the optimal matrix, statistically speaking. And it is now our quest to learn this matrix in a very smart way. Because for large problems, we cannot create this matrix, this optimal expected value matrix, by just enumeration. That is not possible due to computational limitations. So we have to somehow tune our algorithms, try, evaluate, and repeat idea. And in the top right corner of this slide, you see the optimal version one more time. And if we start with a very rough version of this reinforcement learning algorithm, we end up with a very poor learning process. So what we see here are a lot of zeros, and a lot of zeros means that even after playing that game 1,500 times, we still haven't figured out the actual correct value for a location time combination. So we twist it a little bit, bring in some randomness, try out some random moves, and we can improve that. But if we're really good in tuning those parameters, we end up with a solution that is nearly identical to the optimal solution. And that is not only true for this small scale example, but it's also true for problems that are larger. So, final thoughts on the taxicab problem. Even a simple 20 times 20 version is hard to solve optimally, right? So that's why we need efficient algorithms. And reinforcement learning is one of those effective approaches to achieve near optimal solutions. But tuning those parameters, so how the system learns, that is essential, that is tricky. And when we talk about more complicated problems, like problems in that Uber app, when we push that button, it's not just the time and the location, but it's more. It's also the price, it's like the future demand. So there's a lot of more features, so we call them features, that we need to consider to create an abstract version of a state. And that is one of my favorite quotes from this society is, designing such a value function approximation or reinforcement learning approach with the right set of features is both an art and a science. So it's not just about the math. So the math is the one thing, but you can use Python packages to do that. But designing a very efficient machine learning algorithm is more than just math. And that is also what we try to teach here at KLU our students. All right, so back to reality, and that brings me to the last part of my presentation today. So the motivation was that companies like Uber provide customers with a good offer within milliseconds. Right? So at the push of the button, they get a good offer. But the problem is that those decisions occur in a dynamic, so multi-period, and also stochastic, so uncertain environment. But these complex decisions can be modeled as sequential decision processes, and reinforcement learning as one of the three basic machine learning approaches solves those problems by learning a decision's future reward via trial and error approach. And approaches like this are used at companies like Uber. So what they say here is machine learning has been integrated into virtually every facet of Uber's daily operations. So virtually every interaction within the Uber apps involves machine learning behind the scenes. So what they do is they use the data, they use so-called offline learning, where they let servers compute that future reward matrix, but a little bit more complicated, but they learn that future reward matrix many days, and then they can use that matrix in real-world, real-time operations to make decisions within milliseconds. And here are a few examples. So when you log in at this Uber app, machine learning is used to detect fraud signals. So fraud signals like possible account takeovers. When you then search in that app, they have auto-completion. And auto-completion is also based on machine learning. So when you type in N and E, well, it's probably New York. So the system is suggesting you starting in New York, similar to what we know from Google. If we look at the booking, well, the ETA, so the expected time of arrival, that is based on machine learning. So we have some previous information. We have some information regarding the current traffic condition. So based on the historic data, we can come up with a very good ETA. Same with the pricing. When we talk about the trip, the rider-driver matching, that is based on machine learning, same as safe dispatch. And then there's also the so-called post-trip process, where you again have fraud detection, but also as a customer support via chatbots, that's also based on machine learning, right? So chatbots is machine learning. So earlier I talked about reinforcement learning. That was one of the three classes of machine learning, but there are more out there, and chatbots belong to one of those. And the journey is not over yet, right? So this is a figure from an Uber website, so official Uber blog, and what it says that for the last 10 years they have been using machine learning. They started with a very rough version of that. So they call it predictive machine learning with a linear implementation, and then they developed that further. They called it Michelangelo 1.0 and 2.0, and it's called predictive machine learning or deep learning. And right now they started with a new way of approaching those problems, generative AI, but the fundamentals, essentials, they all relate back to what we have learned about tic-tac-toe and about the taxicab problem. And with that having said, I thank you a lot for your attention. Hope to see you all soon. I'm open to all of your questions.
Thank you very much, Arne. I think when I was a child, I took a similar approach for learning tic-tac-toe. But then I tried it with the Rubik's Cube, and I guess the state space was too big, so I took a hammer and then re-put it all together, which was much easier. So if it doesn't work, take the hammer.
Yes.
So I guess we have time for questions.
Yes, if there are some questions.
Yes, please.
I'm dying to know, like the Uber driver, do they follow the recommendation of Uber, or they pick like which one based on their experience and say, oh, if I follow the best offer, then I will get a good journey, or they blindly obey it?
That is a pretty good question. So I've been at a conference a couple of years ago where the chief developer of one of those algorithms at Uber gave a presentation. And he told me that they came up with a very smart algorithm actually learning drivers' behavior. So whenever they reject something which is not profitable to them and instead accept something else, and they do that very often, they will not get that offer again because they don't want cherry picking, because then some customers will never get a driver. So they actually, changed that algorithm a little bit to not providing every driver with every offer, so the driver still thinks, well, it's a smart move because I, not accepting everything but rejecting some of them, but essentially behind the scenes, it's optimized. But it's also going a little bit away from mathematics to behavioral psychology and all this kind of stuff, and a lot of pricing behind. You can work a lot with monetary incentives to actually incentivize drivers to accept something.
Other questions?
I was wondering the training data for these kind of problems, right? You mentioned these kind of value to go or these future profits.
Yeah.
How far do they go into the future to measure these future profit, right? I was for this taxi cab problem, right? The taxi goes from point A to point B, and then there is some information about the future profitability. And you basically, in your example, you said, okay, that would be the next trip, but there is another trip and another trip and another trip. How far is that? Do they need training data for, I don't know, what kind of time frame to learn that? How is it working?
Yeah, that's a pretty good question. So, so a really smart system actually learns and decides at the same time. So whenever we make a decision, we add that piece of information to our training data and maybe get rid of some older training data to get more accurate, maybe very quickly identifying that one of those soccer games is over and that there are a lot of customers. So we could hard program it into the system, tell them soccer game stops at 8 o'clock, but we could also use some smart ways to get the system adapt to that information very quickly. How many periods in advance they actually do that optimization, I don't know. So theoretically, what we use in science, we use a discount factor. So depending on how many periods in advance you look, the value is getting lower and lower. And then it's sufficient to look 10 periods into the future, but yeah.
Just to follow up, because it's the time, right?
Yeah.
One dimension, and the other dimension is the number of drivers, right? Because the question is also which driver to give that right.
Yeah.
Meaning, but also here probably there are only a certain number of drivers who are eligible, let's say, or the most likely ones to pick.
Yeah.
Is there any research which shows a little bit how that system works and how, I don't know, how many drivers they would need? I try to get a little bit of an imagination of how that works.
There probably is. I can't, recall it right now. But the cool thing about machine learning, and later on when we also teach and talk about neural networks, is that we do not have to worry about those details that much. So we shouldn't overthink the problem. And what has been shown is keep it simple. So let the system decide on its own what is important and what not. And there are a lot of efficient ways of, looking at a big set of features, identifying the most relevant ones.
And on top of that, we're talking about stochastic systems where, like, the uncertainty, the further you go away, grows. So it doesn't make much sense to learn from something which is highly uncertain, because the information you can get out of very uncertain, highly dynamic data is very limited. So that typically limits the look ahead that you need.
I wonder, for example, often people use machine learning like a hammer. Right? You're a taxi company, and then you just learn by analyzing the states and then what happened in the past. instead of trying to understand the mobility system on the other side. But there's models that model why people travel from the church to the factory, or not probably, right? Because it's on Sundays, right? It's not what you do. So there's like empirically like validated models that do model them, or like that try to model, forecast the mobility behavior. While I totally believe that Uber probably doesn't use these models, but like rather uses brute force machine learning just to learn from the past instead of like sophisticated trying to understand the system, why they would do that.
Yeah.
Does it often occur to you, or did it occur to you the thought?
So I'm usually publishing the operations research community, and what we do, we really look at the mathematics behind those models. But in reality, I would guess that companies like Uber look at those constellations as well, because if they manage to implement them in a smart way, they could benefit from it. So why shouldn't they do it? But I'm not.
Maybe they use it to train their model in a better way, to artificially generate test instances.
Yeah. So in reality, you would not necessarily learn from artificially created data, but also with real data.
Yeah.
So the agent would be real.
Yeah, it's not a contradiction. Yeah.
And a couple of years ago, I also conducted a study myself where I solved those problems ex post, so retrospectively. I looked considering the case that we would have known everything, so all the uncertainty is gone, what would be the best solution? And I used that optimal solution, so that's retrospectively optimally computed solution in the learning process, and we could show that we increase the learning by significantly. So that was smart. Yeah.
Yeah. So I'm just thinking, if in like the next 50 years Uber introduces autonomous driving, I guess this would then kind of ease the process, because there's no decision making by people to try to profit more, or they take a wrong route, or do more mistakes, right?
Yeah, that is actually, I haven't thought about that, but yeah, you could like in the tic-tac-toe game, it either win or draw, but you wouldn't have any unrealistic behavior.
I don't think that it will ease the problem, because, like if you have autonomous cars, you still need the planning period. Like whether it's a driver or a machine doing the job, really, it doesn't matter. The planning essentially stays the same. There will be other types of uncertainty, right? Like autonomous vehicles also behave strangely sometimes, like you see them braking or accelerating or whatever. So there will still be some uncertainty. The problem will still be there. But it's a good question, and maybe a quick advertisement. In 3 weeks' time, there will be the Cheftreff event here at KLU. So look it up on the KLU website, Cheftreff event, where we will have a guest from Moja, public transport organization, which is actually trying to bring, to extend the public transport in Hamburg with autonomous vehicles, and I will be presenting on the planning for that, or at least some planning challenges, not as a scientific talk, but the general ideas behind that.
And I also agree with you that, coming back to your first question, that it actually would simplify the behavioral aspects of the driver's decision making. So that would be easier, because the computer would do it. And the car just does what the company tells the car to do.
And I think, so from my understanding, Uber drivers usually maybe drive to the middle of the map, so they're easier to reach each direction. But maybe if it's autonomous, they have like a route they can circle or something. So at least there's one car connected to each part of the map, and not everyone's at the busiest section. So.
Yeah. So what Uber does, when I recall it correctly from that talk, they also provide Uber drivers with some reward, so with some money, if they drive without a customer to one of those empty spots.
Actually, you can use machine learning to learn which areas of the city should be provided with the service, right?
Yeah.
Like even if we are ahead of the demand.
Yeah, exactly. Because you have between inner and outer city, morning, afternoon, rush hours, and so on. But again, we shouldn't overthink the problem because the program will learn it. Hopefully.
Okay, any further questions? If not, then thank the speaker again. Thank you.